So thank you for joining us for this presentation about the white paper that we're currently working on around evaluating the limits of door heat exchanger solutions in different applications. And this is specific to OpenRack v3. I am Jabari George, mechanical engineer with GMG. And this is Juan Cacho Alonso, a development engineer at Rittal. We're just two members of the group of collaborators who are working on this white paper. They come from several different companies, so it's not just us. In terms of the objectives and scope, first we just wanted to land the purpose for this. You would have seen a lot of these statistics in other presentations, especially yesterday or over the last 2 days. Data center power consumption. It was just 1.25 to 2% in 2020, and it's grown since then. The current trends show it doubling at least doubling by 2020, perhaps even tripling by some estimates. Consumption is, to meet this consumption, we're going to have to switch to liquid cooling. ASHRAE did a white paper, that's where that diagram was taken from, where they correlated CPU power, compute power, with the available cooling methods. And it's pretty clear, I think we can all agree on that. Door heat exchangers is just one application of liquid cooling in a data center. At the next level, we kind of had to tackle some of the assumptions around usage of door heat exchangers in a data center facility. One of the first assumptions was that you need very cold water, so below W27, or below 27 degrees Celsius, and that you also need very cold air. The reason for that was the limited heat transfer capacity that people would assume a door heat exchanger would have because of the dimensions and the airflow rates. Finally, we also heard that there was an assumption that it was not viable in heat reuse scenarios to use a door heat exchanger. We attempt to tackle each of those assumptions in the white paper that we are writing. So first of all, we show that you can actually achieve a significant airside delta T of 15 to 20 degrees Celsius, even at a 30 degrees Celsius ambient air temperature. You can also get enhanced cooling capacity with warmer FWF facility water supply temperatures. And you can also get a reduced approach temperature. In terms of a scope of analysis, the liquid side, we considered a treated water system at a W27, and I'll get to that after. And on the air side, we considered 30 degrees ambient at a sea level operation with a target delta T of 50 to 20 degrees Celsius. Of course, we considered an OpenRack v3 server operating at 30 kilowatts. And in terms of the door heat exchanger design parameters, we looked at airside delta T's, the supply and return water temperatures, and the approach temperatures. The table on this side, we included that for people who are not familiar with W classes of ASHRAE. So for instance, a W17 class, you would have water temperatures below 17 degrees Celsius, so everything below that will fall into the W class. The other reason why we included this diagram was that if you have a facility and you're operating at one of these W classes, you can also typically have chilled water, so chillers, or a cooling tower. So if you are going through this presentation and you know that your facility has this kind of infrastructure and you're considering a door heat exchanger solution, it may be the data here or the information in this presentation may apply to you. Okay, so that was just a basis. You can look out for these things. I'm going to hand over to Juan, and he will go through the technical analysis.
Thank you, Jabari. So in this technical analysis, we calculate different solutions. Two solutions, the OTS, that is normal rear door heat exchanger, and a new one, a customized heat exchanger for OpenRack v3. So, and this heat exchanger we can analyze in 3 points of view. This is the traditional reactor, the air-assisted, and the hybrid solution. We will analyze the performance, the fan power of the reactor, and we will speak about the CDU. So you can see here, if the performance increase, we will have much more than more power. We can, if we increase the performance, we will be able to decrease the approach temperature. This means by a certain temperature, air temperature going on into the server, we will be able to approach the water temperature, the facility water temperature, to this air temperature going after the server. Why is very important? Because as better the performance is, then we will be able to increase the water supply temperature, and so more hours per year do free cooling without help from chillers and so on. This is an important point. But if you need more power per rack, cooling power, you will be able also to provide this cooling power if the heat exchanger improves the performance. And one question everyone have, okay, you can increase the performance of the reactor heat exchanger, but what happens with the fans? The consumption of energy of the fans of the reactor will increase. Yeah, usually it should be increased, because usually if we increase the performance of the reactor, we increase the performance, increasing the size, the depth of the reactor. This increases the pressure drop, and we know more pressure drop, more energy consumption. But there are much more variables we can change to decrease the power consumption. You can see here in this graph the power consumption of the custom reactor heat exchanger is lower than the OTS, because there are a lot of factors we can change to increase the efficiency. One is if we don't increase in the depth the heat exchanger, but in the height, we increase the performance, but the pressure drop will decrease, maintaining the flow rate. But if we change the fan technology to easy fans, we can decrease a lot the energy consumption of the fans. Or if we decrease the speed of the fans, we decrease also the consumption and increase the efficiency of the system. So there are a lot of ways to decrease the power consumption of the reactor without lose something in performance. So, very important point here we spoke about this is the supply temperature of the water supply temperature. If we are able to increase the temperature to 27 degrees, so we will compare with the OTS, we will be more efficient globally. And it is possible to do that also maintaining the temperature difference into the reactor and in the water side by 8-10 degrees. And this is very important, because if you are not able to increase the delta T, you will increase the flow rate. You can see here the OTS reactor heat exchanger. If you want go to nearly to 27 degrees, you need to decrease the delta T of water. This means you increase the flow rate, the consumption of water, consumption of power of the pump. And we want to avoid it. In case of the air-assisted reactor heat exchanger, the main thinking here is to, if you increase the performance, you can also decrease the supply temperature, water temperature to the cold plates. It means at least that you can increase the power of your rack without paying a penalty with the temperature. And it's not important if the proportion of the total rack power to the cold plates is increasing from 50% to 75%. The supply temperature increase only a couple of Kelvin. So it's not sensible to this point. But if the rear door heat exchanger, the performance increase, you are able to decrease also the supply temperature of the water to the cold plates. So if you want to use the water to other purpose, like something like heat reuse and so on, increasing the performance of the rear door, you will increase or be able to increase the temperature of the water. You can see here that the supply, also the water temperature after the rear door, you can use 45 degrees to other purpose. So 45 degrees is a very high temperature, and if you compare with the OTs, the maximal temperature is something like 40 degrees. This 5 degrees is very important. For example, if you want to use the heat of the rear door for heating purpose or for whatever, this 5 Kelvin could save a lot of energy if you want to use this heat. Also, if increasing the proportion of the liquid cooling in the system from 50 to 90, you are able also to increase the temperature of the supply water. So it's possible as well to save energy in that way. This effect is also enhanced with the custom OpenRAP-V3 rack. So this is a sample with unconstrained liquid flow rate. The impact of the CDU in rack will be to increase the supply temperature of the water. Because the main thinking here is we will increase the supply water temperature as much as possible. And the bottleneck here is the rear door. So if the CDU is between the servers and the rear door, we will be able to supply water at high temperature, something like 27 degrees, and then go into the CDU. The CDU don't need to very high temperature, or can works with very high temperature as well. But if the CDU is before the rear door heat exchanger, we have to decrease the temperature. We lost 5 Kelvin or 3 Kelvin in the CDU, and then we have to go inside the rear door with 27 degrees. So this is a very high impact into the system and so the efficiency. So the takeaways. It is possible to increase the efficiency of the system. It is very possible to increase the performance of the rear door, mostly for the OpenRAP-V3. OpenRAP-V3 is a little bit higher and bigger, the rack. So to increase the performance of the rear door will be possible, and we calculate it. Increase the temperature to the 27 degrees is desirable, and also if you are using cold plates, it is possible to decrease the energy consumption. That was a question for a couple of months for user, say, okay, if you increase the supply temperature of the rear door, the fans of the server will increase the speed. And so that what you save an energy reducing the chiller consumption, perhaps increase the fan consumption of the servers. That case could be solved with cold plates, because cold plates don't need too much server fans. So these results support the OpenRack v3 for future application, and the rear door, the design of the rear door should be usable for several generations of servers. So, if any of you want to join us every 2 weeks in our meetings, please get involved. This is every Thursday at 9 o'clock Pacific time. So, and you have here the mailing list, the links. Please join us and help us to develop this group. Thank you very much.